So I've given you a little bit of a prelude, but first I want to review what the right-hand rule is, and we'll tie all this stuff together here in a second. So if this definition doesn't make sense, which I don't expect you to think it makes sense at this point, just stick with me and it'll make sense here in a few minutes, okay? What is the right-hand rule? Just to review. If I have a vector, and this vector is A, okay, and I have another vector, and this vector is a different vector, and so it's called B, okay, and I'm going to cross B crossed with A. This X is not multiplication from third grade. This X is actually called the cross product. B vector crossed into A vector, okay? I haven't even told you how to actually do this calculation yet, but as far as the direction goes, when you take B, okay, and you cross it into A, this is why it's called the cross product. Take your right hand, okay, cross B into A. So you actually move your fingers and cut through B and finish into A and kind of curl your hand like this. The direction of your thumb is going to be the direction of these two vectors crossed together, okay? So this operation, B crossed into A, returns a vector. That's what it says. It returns a vector that is perpendicular to the two initial vectors, according to the right-hand rule. So if I have B and I'm crossing it into A, I take my fingers, I cross it in, and I gain a third vector. And that third vector, in this case, comes straight out of the board, okay? And so that third vector, which is the answer to this cross product, it is perpendicular to the two initial vectors because when I cross it, you see, any vector coming out of the board is perpendicular to the two initial vectors, okay? Okay, so I don't expect this to make total sense yet because we have a few more things to cover before it does make sense. But one thing I want you to remember is for the dot product, we had two vectors, we were dotting them together, and it returned a number, okay? That was sort of a number that was related to how those vectors line up, so to speak. You have one and you dot it into the other, and it gives you an answer related to how much those vectors, the only component you care about is the component of the two vectors multiplied together in the same direction, okay? This guy does not return a number. The cross product returns another vector, okay? So that third vector, that's the answer to the cross product, is going to have a magnitude and it's going to have a direction, okay? I'm telling you right here that the direction of the cross product is always going to be exactly perpendicular to the two vectors you started with. So anytime you draw two vectors on your piece of paper, the cross product's always going to come out of the board or go into the board depending on the right-hand rule. So if it's B cross A, we curl it this way, B crossed into A with our right hand, it comes out of the board. If I had written it as A crossed with B, okay, like that, then I would cross A into B and I would be going the other direction, cutting into A first and then into B, and then the third vector, the answer to this cross product, would be a vector going into the board, okay? So the direction is a result of the right-hand rule. No math involved in that right now, just conceptually, it's just that's what it is, okay? I haven't told you how to calculate the magnitude yet. We're going to get to that in just a second. Okay, so how do you calculate the magnitude of that cross product? We've talked about the direction. It's perpendicular to the two initial vectors according to the right-hand rule. We've talked about that. How do you calculate the magnitude of that vector? The magnitude of the cross product of two vectors, this is the magnitude of the cross product of two vectors, is equal to the magnitude of A vector times the magnitude of B vector, okay, times the sine of the angle between them, okay, the sine of the angle between them. Okay, so you can see right away that this operation is going to produce a number because we know how to calculate the magnitude of the A vector. That's basically the distance formula. We've talked about that. We know how to calculate the magnitude of the B vector, and we already talked about that. And we know how to calculate the sine of the angle between them, assuming we know what the angle between them is, okay? And so this is how you would calculate the magnitude of these two vectors, okay? If you know what A and what B is, you can just put it in here, and if you know what the angle between them is, you just punch it in here, and you'll get a number out, and that number is the magnitude. So with this calculation, you'll know how to calculate the magnitude of the cross product. Using the right-hand rule, if you have something drawn in your paper, you can calculate or get a feel for the direction, okay? And so you know the magnitude, you know the direction, you get the answer, which is the cross product of the two vectors is a vector, okay? Now notice this looks an awful lot like the cross product, just as an aside more than anything else. A dot B was equal to magnitude of A times magnitude of B times cosine of theta. The only difference being here is A dot B is not a vector. A dot B is a number. So you calculate this times cosine of theta, and you get a number, and that's the answer. That's the dot product. But when you do the cross product, you do a times b, magnitude of a times magnitude of b times the sine of theta, but that's only the magnitude of the vector. That's the answer. That's not the actual full answer. You still have to have the direction here, which is given by the right-hand rule. So that's conceptually what we're doing. Now what I want to do next is I want to give you a motivation. I'm going to move to the other side of the board. I'm going to give you a motivation for why you would care about the cross product using a real life example, okay? And then we're going to come back to the math a little bit and actually crank through doing some real cross products and get some practice with actually calculating the cross product when you have some real examples, okay? So when would you actually use this guy? Well, consider for me here, what if I had a wrench, okay? Here's a wrench, if I can draw a wrench properly. This is my wrench. It's not a very good wrench, okay? But here it is, okay? So I'm trying to loosen some bolt in here, okay? Or some nut or something. I'm trying to do that. And so I'm going to do that by applying a force to the wrench, okay? Well, you all know from your experience that the way to make this thing move is to grab the handle and pull down or to push up, okay? And we all know from experience that it's pretty stupid to grab this thing at an angle and push it this way, or grab at an angle and push it this way. We all know that the best way to loosen this nut from our experience is to grab it exactly perpendicular to the handle and then push it or pull it. You don't want to go at an angle because you're wasting effort. We all know this, okay? But mathematically, what you've discovered for yourself over the years is something related to the cross product. So let's figure out what that is, okay? Let's say that you were to actually apply a force at an angle, which we all know that we really shouldn't do because you're wasting effort, right? But let's say you do, right? And let's go ahead and we'll call this force F. Okay, this force is F, and force has a magnitude and a direction, so that force is a vector, okay? That force is a vector. And what you can see from the drawing is that this angle right here, right there, is the angle between this force vector and, you probably haven't realized it yet, this is also a vector, R, okay? And this is just simply the length of the wrench. I mean, that's all it is. It's a vector. It has a direction because the wrench is laying horizontally, and it has a magnitude, which is just the length of the wrench, okay? Now, from your basic physics, you may or may not remember that the torque that you apply to something, is R, which is basically the length of the object you're trying to grab and move, okay, crossed with the force you apply on it, okay? This is equal to the torque, okay? So what I want to actually do is I want to say that torque is equal to R cross F, which is equal to what we've already been talking about, which is the magnitude of R times the magnitude of F times the sine of theta, okay? I should say the magnitude of the torque, okay? The magnitude of the torque, okay, is the magnitude of R cross F, which is the actual amount of torque you're applying to this nut here, is magnitude of R times magnitude of F times the sine of theta, okay? Now think about what's going on here, okay? If theta, which is the angle that I'm applying this force, if theta is equal to 90 degrees, so I'm actually pushing exactly down on this thing, then sine of 90 is 1. Sine of 90 degrees is 1. Sine of pi over 2 is 1. So in that case, the torque is going to be a maximum. If I hold the force constant, and of course my wrench is a constant length, R times F, length of R times length of F, times sine of theta. If I push exactly down, then this angle will be 90 degrees, which is pi over 2, and this torque will be a maximum, okay? The magnitude of that torque will be a maximum, okay? But if I start changing that angle anything other than 90 degrees all the way down, let's say I make it 0 degrees. Let's say I'm just really not very smart, and I'm going to grab this wrench and push this direction. I'm going to grab it, and I'm actually going to push it to the right. We all know from experience that we're not going to get any torque on that bolt. And the reason is because if I push this direction, then theta is 0, right? And sine of 0 is 0. So your torque is 0. So if you apply a force exactly along R like this, then you get 0 torque. And torque is what breaks the breaks the nut for you and lets you turn the nut. Okay, it's kind of like angular force, right? So you have to be able to exert something outside of 0 degrees. So we've all learned through our experience that 90 degree is the sweet spot, and the reason it's the sweet spot is because the sine of 90 degrees is 1, and that makes the torque a maximum. And we've all learned this without actually knowing what the cross product is, but that's a practical example of what the cross product is used for. And that's why we define it this way, because the torque we only, for calculating the torque on an object, we only care about the magnitude of F acting in the perpendicular direction like this, okay? Another way of saying that is, let me switch colors yet again. Another way of saying that is, this magnitude right here, this is F times the sine of theta. Just look at the triangle here. This is a vector F, okay? And this is an angle. And if you take F times the sine of angle, then this guy is the component of F acting down. And this guy is the component of F acting over like this. We don't care about him. What we're saying is that the torque is only dependent upon and only responds to the component of the force acting perpendicular to R, okay? That's why it's R times F times sine of theta. The sine of theta is what chops the force down and makes it only the perpendicular component of it that matters at all for the torque. So you see a little bit of duality here. You see a little bit of symmetry here. When you're talking about the dot product, you only care about the component of the force acting along the other vector, acting in concert with, in the same direction as the other vector. That's all you care about for the dot product. And there's certain problems where you want to dot two vectors together because that's what the physics tell you matters, okay? Likewise, for the cross product, we only care about the component of F, this guy, acting perpendicular to this vector. So it's a duality thing. It's not the same thing, but it completes the circle. So now we care about the component of F acting perpendicular to the other vector, and so we have a slightly different definition. R times F times sine theta, that gives us the magnitude of the torque. Now, torque returns a vector. I shouldn't say that. Any cross product returns a vector. So if you were going to calculate the torque as R cross F, the torque is equal to R crossed with F. The cross product always returns a vector, and the cross product is given by the right-hand rule, which is what we've already talked about. So you would take R, you would cross it into F with the right-hand rule, and the answer is going to be the vector is always going to be coming out of the board. So anytime you're dealing with cross products, the resulting vector you get mathematically is always going to be perpendicular to the two vectors you started with. So now you know how to calculate the direction by just using this simple formula. The magnitude of the resulting vector of this guy, and the direction is always the cross product, R cross F. And that's just an example there. So that's a real life example of why we care about cross products, because they turn up in real life all the time when you want to cross two vectors together. Okay, now that we have an understanding of what we would use a cross product for, and we've talked a little bit about it. We've talked about how to get the magnitude of the crossed vectors, and the direction is just the right-hand rule. We've talked about that, but that kind of presupposes that you know what the angle between these vectors is. And a lot of times in your physics book, you'll know that, because in your physics book, they'll give you a wrench, and they'll give you a force, and they'll give you an angle, and they'll say, what's the torque, okay? Well, you're not always given that. You may be given this vector in component form, ijk form. You may be given this vector here in ijk form, and you may not know what the angle between the vectors are, and that's going to prevent you from calculating the cross product here. So we need to figure out how to do that. So in order to set us down on that path of how to calculate the cross product in sort of a bulletproof way, what I want to do first is I want to give you a little bit more practice in thinking about cross products, okay? But we will get there. We'll get to the point where you can take any ijk vector and any other ijk vector and cross them together and get the answer, okay? So here's your familiar coordinate system. You have your x, your y, and your z, okay? And we've already talked about these things called unit vectors, okay? We've already talked about the fact that the I unit vector is right here, I hat. The j unit vector is here, and the k unit vector is the one that corresponds to z. I, j, k are just labels, unit vectors of length 1 in the x, y, and z direction. Okay, so looking at this picture, let's get a little practice with doing this cross product stuff, just sort of with a nice picture here. Okay, what if I asked you, what is the I unit vector crossed with the j unit vector? Now don't be scared by these little hats. These are just vectors along the axes of length 1, okay? So each of these vectors, by definition, these unit vectors, they have a length of 1, you know this, okay? So what would I cross j be? Well, we know it's magnitude of the first vector times magnitude of the second vector. Well, the magnitude of this vector is 1, the magnitude of this vector is 1, so that just gives you 1. 1 times 1 is 1, and it's sine of the angle between, okay? That gives you the magnitude, okay, But look at this, I and J are always 90 degrees apart because they're on the axes here. So because they're 90 degrees, sine of 90 is 1. So the magnitude is going to be 1, okay? And the direction is going to be, let's use the right-hand rule, I cross J. If you can imagine cutting into I like this and crossing into J like this, you'll be pointing up. So the answer is going to be a unit vector of length 1, because 1 times 1 times 1, magnitude of this times magnitude of this times the sine of the angle between them is 1, okay, and pointed up. Well, that means that the answer to this I cross J is going to be the K vector, okay, simply because of the right-hand rule like this, okay. Now, similarly, J crossed with K, okay, if you look at J, okay, and cross it, cut into J and cross into K like this, you'll be pointing out of the board, and if you look at the drawing, that's simply the I vector. So J cross K is the I vector, okay? And let's do K cross I, okay? Taking K and cutting into K first and then cutting into I, you'll be pointed to the right, and that's going to be the J vector, okay? And then one final example, if you had K crossed with J, what would that be? Okay, you have K and you cut into K and you cross into J like this. You're pointing into the board. Well, notice that the I vector comes out of the board. That's a unit length coming out of the board. Well, I'm pointing into the board. So the answer is not going to be I, it's going to be negative I, because the unit vector going through the board is exactly negative of the one that comes out. So instead of I hat, it would be negative I hat. So you see, you're using the right-hand rule. I cross J, crossing I into J gives you K. J cross K gives you I. K cross I, going down like this, crossing K into I gives you J. And then K into J, just as an example, goes through the board, which is negative I, okay? And there's lots of other ones you can pick and practice. And using this little drawing really helps you visualize it. If you don't have this drawn and you're trying to do this, you're going to probably mess something up eventually, okay? So I'm just giving you practice by using the right-hand rule. The resulting vector you get is always perpendicular to the two you started with. That's what the definition says. The vector returns a vector that's perpendicular to the two initial vectors according to the right-hand rule. That's all we're saying here. And the magnitude of the resulting vector is given by this, and this follows that exactly. That's what we've done here. Now, we want to complete the circle, and I want to give you a bulletproof way to calculate the cross product of any two vectors. Maybe I don't know the angle between the vectors, okay? Maybe I just know that they have some ijk components, and I don't know exactly anything other than that. I've never drawn it. I don't know what the angle between them is, but I would like to calculate the cross product, okay? Here is the answer to this. The general way to calculate the cross product, A, and we're going to practice this, so if it looks a little crazy, don't get too worried about it. A cross B is always equal to exactly the determinant. This is for three-dimensional vectors that are more complicated than your 2D vectors you usually see in physics. The determinant of the matrix, okay, given by this. You have I hat up here, J hat up here, and K hat up here, okay? And you have A1, A2, A3, and B1, B2, and B3. The determinant of that matrix. I know that makes no sense at all right now. We're going to do some problems and make it really clear. It's not too hard. But what you're doing is you have a 3 by 3 matrix. The first row is just the unit vectors I, J, K. The next row is the components of the A vector. Remember, A in general has 3 components. X component, Y component, Z component. We call them A1, A2, and A3. So you put those numbers in this matrix, okay? B has 3 components. We call them B1, B2, B3 for the X, Y, and Z components of this. We stick it in the matrix. We put all this either into a computer or calculate it by hand, hit the button, or crank through it mathematically, and what you will get is you will get another vector, and I'll show you how you do that in a minute. You'll get another vector, and that vector will be the cross product, and that vector, by the way, will always, by definition, if you do this right, be perpendicular to A and B, just like the definition says. And the length of that vector that you calculate by doing this will always be, by definition, A times B times sine of theta. Even if you don't know what theta is, you're always going to calculate the right vector in the answer because that's the way the math works out. Okay, now I'm going to give you one more tidbit of information before we actually solve a problem. This is the kind of thing you can talk about all day long and it doesn't really help. But I want you to recall something because we're going to use it a lot when we calculate the determinants of these matrices like this, okay? Recall that the determinant, okay, of a 2 by 2 matrix, A, B, C, D, has nothing to do with this. So don't think I'm trying to tie it together. I'm just telling you, recall that the determinant of the 2 by 2 matrix like this is equal to A times D minus B times C. And if you forget that it goes in that order, okay, you start here in the upper left corner and you multiply this direction, and you start over here and you multiply this direction. So it's AD minus BC. That's how I remember it, okay? So we're going to use that a lot. We're not going to explain exactly how you use it right now, because if I start trying to do that, theoretically, you're going to get confused. What we want to do next is we want to actually solve some problems. So try to burn this into your head. All we're doing is, for the next few problems, we're going to show you a couple vectors, and we're going to actually cross them together by calculating the determinant of this matrix. We're also going to use some of these other definitions here to show you how it all ties together. Okay, so for the first problem, simply put, the problem is going to say find A crossed with B, which is the cross product of these two vectors. We know it's going to return a vector. We want to find out what that is. The A vector is given by I hat plus J hat, okay? And the B vector is given by J hat plus K hat, okay? So the component, the way you read this is the X component of this vector is 1, the Y component is 1, and there is no Z component. Okay, for the B vector, there is no I here anywhere, so the X component is 0, the Y component's 1, and the Z component's 1. Okay, so that's what you're saying here is these I and J and the coefficients in front of them really just tell you the X, Y, and Z components of these vectors, and we've talked about that before. Now, how do we calculate A cross B? Notice that we do not know the angle between these vectors, and frankly, I wouldn't even be able to tell you how to calculate the angle of those vectors without using the cross product in the first place. I mean, you could probably draw it and try to figure out what the angle is between them, but I don't know what it is. So the definition of the cross product as A times B times sine of theta doesn't really help me too much. And not only that, how would I tell you what the direction between, of the resulting cross product is? I need to be able to use the right-hand rule to be able to do that, but I can't visualize exactly what these vectors look like very easily. And as they get more components, they're going to be even harder to deal with. So we're going to use our bulletproof way that always works, okay? And that's the determinant way. You're going to have to learn how to do it, so just bite the bullet. Okay, A cross B, okay, is equal to the determinant of the following matrix, and I'm going to walk you through how to do that. All you do on your paper is you literally write I, J, and K, and if you go back to the previous screen, you'll see that that was in the first line, okay? The next line are the components of the first vector in the cross product, because you're crossing A into B, so you have to work with the components here, okay? The X component is 1, the Y component is 1, and the Z component is 0. So I just put 1, 1, and 0 there, okay? For the B vector, there is no I hat, so there's no X component, so I put a 0. The Y component is 1, and the Z component is 1. Okay? So congratulations, you've set up the problem successfully. The determinant of this matrix will yield a vector that will be, by definition, the cross product you want. Okay? But the question is, how do you actually calculate that determinant? And it may be a while, it may have been a while since some of us have studied that. So what we're going to do is do it step by step. This is the way you do it, okay? The first thing you do, you just put an equal sign here, and the first thing you do is you put the I hat down, because what we're going to do is work on the I component first, the X component first, okay? What we're going to do is we're going to work on the answer. The vector is going to have an ijk component, and we're going to work on the I component first, which is the X component of the resulting vector. So all you do is you look at your matrix and you say, okay, well, I have an I hat here, so I'm going to put my hand over this column because it has an I hat, and I'm going to cross out through this column. So I'm going to ignore everything at the top, and I'm going to ignore everything here, and I'm only going to look at these 4 numbers, okay, right here. So in order to calculate the component of I calculate the determinant of these 4 numbers, which is what I told you would need to know, okay? Remember, the determinant of A, B, C, D is AD minus BC. It goes as an X, AD minus BC. So because I'm working on the I component first, I put ignore this row and I ignore this row, and I'm only looking at these 4 numbers. So I put a bracket here and I say, okay, going as according to this formula here. 1 times 1, and I'm going to write it all out because I want you to see every single step of the way. 1 times 1 minus going this way, 0 times 1. Okay? Congratulations, you've just found the I component, the X component of the answer. Okay? Pretty easy. You just have to get used to it. Okay? Now, what we're going to do next is work on the J component, and so I'm going to mark through this column because I don't want to look at that, and I'm going to also mark through the top as well. That's just the way you do it. The only trick to this whole thing is when you work on the J component, you have to put a minus sign. So you put a minus J, open a bracket, okay? And now I'm crossing through this, so the only numbers I care about are these two and these two. These are 4 numbers that are sort of look like a 2 by 2 matrix. So ignoring this and ignoring this, I'm going to calculate the determinant only using these 4 numbers here, okay? So starting up here, 1 times 1 minus 0 times 0. Okay? And don't worry, we're going to review all of this in a second. Okay? Now I'm going to work on K. I go back to using a plus sign, K. Okay? I'm going to mark through this column because that's where the K is, and I'm going to mark through this, and now I'm only looking at these 4 numbers. Okay? So going with the X, 1 times 1 minus, going this direction, 1 times 0. Okay. Let me go ahead and simplify the answer and get the answer, and then we'll go back and trace through it and make sure everybody gets it, okay? In the I direction, what I have is 1 times 1 minus 0, which is going to be 1. I have a minus sign here, so I carry it. The J direction, I have a 1 times 1, which is 1 minus 0. And in a K direction, I have a 1 times 1 minus 0, so I have a 1 here. So the answer is going to be, just because this is a 1, I'm going to write it as I minus J plus K. This is the answer to A crossed with B. Okay? I minus J plus K. So, before we go back and trace through how we got the answer, okay, what we have found is we found that the cross product of these 2 vectors is another vector. We told you that that would be the case. You always get a vector when you cross 2 vectors together. If you were to actually plot A and B, and try to actually construct a vector representation and also find plot the answer, you would find that this vector is indeed exactly perpendicular to the 2 vectors here. You know, it would be something like in 3-dimensional space if vector A was over like this and vector B was over like this, the answer, when you plot it, would go directly perpendicular to both of them. That's what the answer is. And if you were to also calculate magnitude of A times magnitude of B times, if you somehow magically knew the angle between them, okay, you would take the sine of the angle times this, you would get the magnitude of the cross product, and if you took the magnitude of this vector, that would agree as well. So what I'm trying to tell you is, this is the answer. This is the vector, okay? And if you go and do that every time, then you'll always get the right answer. So if you have the vectors in component form, IJK form, you pretty much have to do this. If you know their magnitudes and you know the angle between them, you can easily calculate the magnitude of the cross product just by doing A times B times the sine of theta. But we don't know what theta is. We were never given theta, so we couldn't do that. Okay. Now let's trace through how we did it. A cross B is always going to be defined as the determinant of a matrix. You always put I, J, and K in the top row, and then for the next row, you fill in the components of the first vector, A. You had a component 1 for X, 1 for Y, and nothing for Z. Okay? And then you fill in the components of B. Nothing for X, 1 for Y, 1 for Z. So all you have to do is find the determinant. Now, when you go back and revisit your matrix algebra, your linear algebra, okay, you will find the general form for calculating the determinant of a 3 by 3 matrix. I'm showing you what that is here. I'm not proving it to you. I'm not asking you to trust that it makes sense or that this is just intuitive, because it's not intuitive. But what I'm boiling it down and telling you is this is how to do it. And if you look in a linear algebra book, this will be how they tell you to do it. Probably they'll have a big, long formula that will look really odd and foreign to you. But what it's boiling down to is the following. To work on the I component of the answer, you put your hand or your pencil or something over the column with I and also over the column up top, kind of crossing out everything here. Whatever 4 numbers you're left with, you calculate the determinant of this, which is given by this little relation that we talked about before from your basic algebra, and we did that inside the brackets here. That is the answer to the first component. To work on the J component, we do the same thing. We put a line over here and over here, so all we're looking at is the remaining 4 numbers. And we calculate the for j, we calculated the determinant that way. 1 times 1 gave me the 1, minus 0 times 0 gave me the 0. So that's the component for j. The only thing that's kooky about it is when you work on j, you always have to stick a negative out here. That is just the way it's derived. If you were to crack open a linear algebra book and look at the proof of how to calculate this determinant, they could show you and walk you through why there's a negative sign here. I'm not making any attempt to prove it to you, but this is what you do, okay? And then when you get to the k component, you cross out the column with k and the row with k. You're left with these 4 numbers. And you calculate the determinant of those 4 numbers, which you do right here in the brackets. You do your simplification, and you'll get something with I, something with j, something with k, and that is the answer. And this vector is the cross product of these 2 vectors. And this has a magnitude according to a times b times the sine of theta, and it has a direction that's perpendicular to these 2 vectors. Okay, so the next problem is if a vector is 2 times I, or 2 in the I direction, plus 3j minus k, and b vector is negative I plus 4j plus 5k. Okay, now what we want to do first is we want to calculate what a cross b is. Okay, just like we did before. So we have a crossed with b. Okay, what we do is we construct our determinant just like we did before. Let me switch colors. Okay, so it's going to be equal to the determinant of the following matrix. You always put I at the top, and j and k at the top. Okay, now you just fill in components. What are the components of A? That's what goes in the next line, and then the components of B go on the next line. So you have 2, 3, and negative 1. And for the B vector, you have negative 1 here, 4 here, and 5 here. Okay, so all we have to do now is calculate the determinant of this matrix, and that is the answer. That is the actual cross product answer that you're going to get. Okay, so let's do that. Okay, so what we're going to do first, we're going to say A crossed with B is equal to, first we're going to work in the I direction. So we're going to cross this column out because it has the I in it, and we're going to cross this row out because it has the I in it. Okay, so we're only going to be left with these 4 numbers here, and we have to calculate the determinant of that. So remember, the determinant goes as an x. It goes down to here and then over to there. Okay, so crossing through this and through this, we're left with these 4 numbers. So we start up here and start drawing our x. 3 times 5. I'm actually going to write the whole thing out instead of just putting the multiplication down because I want you to see. 3 times 5 minus negative 1 times 4. I would encourage you to do the same thing because if you start skipping steps, you'll have a hard time tracing your answer. Okay. To work on the j component, I always have to put a negative and then put j. That's just part of the way it's derived, and that's how you do it. Now I cross out the j column and I cross out the top row, and I'm left with these 4 numbers. And I have to calculate the determinant of that. 2 times 5 minus negative 1 times negative 1. Okay? And finally, plus k. Okay, working on the k component, I cross through this column because that has the k in this. I'm left with these 4 numbers. So I calculate the determinant here. 2 times 4 minus 3 times negative 1. Okay, so that's it. All I have to do is do simplification and I'll have the answer. So I'll have A crossed with B is equal to, in the I direction, okay, I'm going to have 15, 3 times 5 is 15, plus 1 times 4 is 4, because negative times negative gives me that positive. Okay, I'm going to have a minus j, because I have a minus sign here, and on the inside I'm going to have 10. This is going to make a positive, so it's going to be negative 1, so it's going to be minus 1. Okay, and finally k, the k direction, this direction here, 2 times 4 is 8, and then I'm going to have plus 3. Okay, so finally I think we're in a position to do our final simplification here. Okay, 15 plus 4 is 19i, so that's 19 in the x direction essentially. Okay, and then I'm going to have minus 10 minus 1 gives me 9, so it's 9j, so 9 in the y direction effectively, plus 8 plus 3 is 11, so it's 11 in the k direction, which is the z direction. So the answer to the cross product is 19I minus j plus 11k. And this vector, if you were to actually try to draw it and look at it, is exactly perpendicular to these two vectors. Now you see what I'm getting at here. You see what I'm getting at? When we talked earlier about the cross product, I said it was the magnitude of the first vector times magnitude of the second vector times the sine of the angle between them. That gives you the magnitude of the cross product answer, okay? Well, I have no idea what the angle between these vectors are. I just can't look at it and figure it out. I doubt very many people can, okay? You really can't do that. So when you're given vectors in ijk form, which is almost all the time you're going to have them like that, you really can't use that definition too much to calculate the magnitude of the cross product. You have to use this determinant thing, and this gives you the vector. And how, by the way, how would you be able to tell by glancing at it that this vector was perpendicular to the first two? I certainly couldn't figure that out. Okay, you could do it by trying to plot something, I guess, but it would be difficult. But that is indeed the case, okay? So the next thing I'm going to ask you as a follow-up to this problem is, how do we calculate the angle between these vectors? What if the problem said, calculate the angle between these vectors? Let's forget about this stuff. What if the problem actually said on your test, here's A and here's B, calculate the angle between the vectors, okay? Well, you have to know how to do that. So now that we know what the cross product is, we've calculated that, okay? And we know how to calculate the magnitude of A and the magnitude of B. We've done that before. We know how to do that. And we know that the cross product is equal to magnitude of A times magnitude of B times sine of the angle between them. We can calculate the sine of the angle between them, and that will allow us to calculate the angle, okay? So if the problem said what is the angle between them, what we're going to end up using is the magnitude of A cross would be is equal to the magnitude of A times the magnitude of B times the sine of theta. We know what this is. Well, we know what A cross B is. We're going to calculate the magnitude of it in a second here. We know what A is, so we calculate its magnitude. We know what B is, we calculate its magnitude. So we know everything we need to know to calculate the sine of the angle, and we just take the inverse sine and we'll find the answer. Okay? So let's do that right now. Okay? What is the magnitude of A crossed B? Well, we just found what the cross product was. The cross product was this vector here, 19I minus 9j plus 11k. So how do we calculate the magnitude of that? The magnitude, remember, is just the square root of every component squared. So it's 19 squared plus negative 9 squared plus 11 squared. And we do that math and we take the square root, and that's going to give us the answer, okay? So what we're going to have here, okay, is the square root of 19 squared is 361 plus 9 times 9 is 81 plus 11 squared is 121, okay? And so what we're going to get here is the square root. When you add all those things together, you get 563. So what you're going to get is 23.7 roughly, okay? When you actually take the square root. That is the magnitude of A cross B, okay? Okay, that's the magnitude of A cross B. So we have one of the things that we need to continue, okay? Now, what is the magnitude of A? Okay, we're going to do the same thing. A is given by this vector, 2I plus 3j minus k. So we just take the square root of each component squared. So it's 2 squared plus 3 squared plus negative 1 squared. And I know as well as you do that the negative 1 is going to give me a positive, but I just put the component in there so that when I'm tracing through my work, even though I know a negative times negative is going to give me a positive, I put it in there like this so I know what I did, okay? So what I'm going to have on the inside here, 2 squared is 4 plus 9 plus 1, okay? And that's going to be the square root of 14, okay? The square root of 14, which is 3.7 roughly. So the magnitude of A is roughly 3.7, okay? Now let's find the magnitude of B. That vector was given by negative I plus 4j plus 5k. So we're going to do the same thing we did before, square root of negative 1 squared plus 4 squared plus 5 squared. So that's the square root of 1 plus 4 times 4 is 16, 5 times 5 is 25. Okay, and so what I'm going to have here is the square root of 42, and when you do that math, you get roughly 6.5. Okay, magnitude of b. Now, why do we do all this stuff? Let's remember what we were trying to do. We're trying to find the angle between the vectors. We know what the magnitude of the cross product is and what the magnitude of the initial vectors are, so now it's a matter of just plugging in and solving. Okay? So coming back up here and applying this formula, okay, the magnitude of A cross B was given by 23.7, so I write 23.7. The magnitude of A was given by 3.7. The magnitude of B was given by 6.5 times the sine of theta. Okay, so when you do this math, what you'll find is the sine of theta is equal to 0.978. And so theta, when you take the inverse sine, is 78.1 degrees. Okay, so what you found is the angle between the two vectors. So this is how you would go about solving the problem and saying, what is the angle between the vectors? Okay, you would start out and you would have no idea how to do that, but you would know right away that you can calculate the cross product. Okay, and you can calculate the answer to the cross product. You can also calculate the length of that cross product, which we did here. We calculate the magnitude of the two vectors and use the definition of the cross product. The length of the cross product is the length of A times the length of B plus times sine of theta. We use that fact to get the theta. Now, if the problem just said find the angle, you could use the cross product to do that. You could also use the dot product. I mean, you could calculate the dot product of these two vectors and then use the other definition of dot product, magnitude of A times magnitude of B times cosine of theta, and you can also find the angle. A lot of times on the test, they'll ask you something they'll force you into using the cross product. They'll say, use the cross product to find the angle between the vectors. To force you to actually do this so that they see that you know how to do that. So you have to be able to know that. But there are many ways to do a problem. So you can use the cross product to find the angle or the dot product to find the angle. But that's basically what we're doing here. Let's go ahead and do one more thing, and we'll get the hang of it here. Okay, so the next problem is if you have a vector, which is 3i plus 4j plus 12k. And let's say I asked you to do something crazy and said cross it into another vector that's exactly the same vector. Okay? Well, you know how to do it mathematically, but what do you think is going to happen? Well, these two vectors have exactly the same components, and that means that these two vectors are pointed in exactly the same direction. Okay? And so if they're pointed in exactly the same direction, that means that these are parallel vectors. Okay? Parallel vectors. Okay? Now, it turns out that because of the definition of the cross product, okay, being A times B times the sine of theta, if two vectors are parallel, okay, if two vectors are parallel, that means the angle between them is 0. Okay? So if I put a 0 in here, sine of 0 is 0. So if I get a cross product of 0, I always know my vectors are parallel. Okay? We had a similar rule to find out if vectors were perpendicular in the dot product. Here's how you figure out if they're parallel. If you cross two vectors together and you don't get a result, then you know that they line up exactly, okay? And they're lined up like this. And so the cross product, remember the definition of it is you're multiplying the vectors, but you only care about how much of the vector is perpendicular to the other vector. But if they're both exactly lined up, there is no such component of that vector perpendicular to the other one if they exactly lie on top of each other in the same direction. So the cross product is going to give you 0. So that's what we expect to happen because we know that these are parallel vectors. Okay, but I don't want to use this to calculate that because I don't. Even though I have an idea that they're parallel, I don't really know for sure the angle between them. I mean, I can guess by looking at the components, but I want you to go through the full glory of the other way just for practice. Okay. So how do we calculate the cross product? And it should turn out to be 0 if our intuition is right. Okay. So we'll have A cross with B is the determinant of the matrix given. You have I, J, and K. And all we do is we look at the components of A and put them in the next line. So we have 3, 4, and 12. And the components of B are exactly the same thing, 3, 4, and 12. So we have to calculate the determinant of this. Okay? So remember that for a simple little 2x2 matrix, A, B, C, and D, I just had this written down a minute ago, that the determinant, okay, is AD minus BC. It goes like an X, AD minus BC, okay? So let's do that here. Let's do that right now, okay? I'm going to work on the I component first. Okay, so inside the brackets, I'm going to cross out this column here and cross out this column and work on this. 4 times 12 minus 12 times 4. Okay? Now, it's no secret that this is going to give you a 0 in the middle here. Okay? But I'm just doing it just to show you rigorously how to actually tackle it. To work on the J component, you go next, but you always have to put a negative sign out in front of your J and calculate that. Now you cover this column up here and cover this column up, so you only have these two numbers and these two numbers. Doing the determinant, 3 times 12 minus 12 times 3. Okay? And then finally, for the K component, you cover up this column and this, so you have these four numbers, 3 times 4 minus 4 times 3. Okay, so I think you can see pretty clearly that what you're going to have in the I direction, you're going to have 0. So you have 0I, right? In the J direction, you're going to have 0. So I'll put minus 0J. Okay, in the K direction, you're going to have 0. Okay, 3 times 4 minus 4 times 3. So what you have shown is that the answer is 0I minus 0J plus 0K. But what this effectively means is I don't have any component in X, I don't have any component in Y, and I don't have any component in Z. So this vector is basically 0. There's no length to it because I don't have any length in any direction, so there's nothing to it. So the cross product is 0, which is exactly what we thought we would get because these two vectors are parallel to one another, which means that the angle between them is 0, which means that if I use the other definition for the magnitude of the cross product and the sine of the angle between them, the angle is 0. So I've proven right there that sine of 0 is 0, so these guys are parallel. Okay, so we've covered a really important topic in this section. That's the topic of the cross product of two vectors. Okay, very important to remember how it plays into the big scheme of things. The dot product is when you're multiplying two vectors, and the physics of what you're trying to do is that you only care about how those two vectors line up with one another. Okay, and so the component that you multiply in is only the component in that direction. And so you get a number back. That's the dot product. Okay, the cross product does not return a number, it returns a vector. Okay, the length of that vector that it returns is equal to basically multiplying these two vectors together, a times b times the sine of theta, and that sine of theta really means what you're interested in is how much of these vectors are perpendicular to one another. Think about that wrench, the torque. You're trying to maximize the torque, so it only matters the component of the force that you're pulling perpendicular to the other vector. Okay, that's why you use a cross product. It returns a vector, the length of which is a times b times sine theta, the direction of which is the direction perpendicular to the two vectors to begin with. Okay, and the cross product, the right hand rule gives you that, a cross b across a into b, that gives you the direction. Okay, but if you don't know the angle between them, so you can't use that, if you can't use that because you don't know the angle between them, if you only have it in component form, then the bulletproof way to always calculate the cross product is to take the determinant of the 3 by 3 matrix laid out like this. You've got your ijk unit vectors and your components of your two things you're crossing, and I've shown you the method to actually calculate the determinant of that matrix. That'll always return a vector that's going to have your components, and that vector is perpendicular to the initial two vectors, and that vector does have a length that goes according to a times b times sine theta. So everything makes sense and is self-consistent with each other. And when two vectors are parallel with one another, the cross product will always give you 0 because the angle between them is 0. We talked about that. So that's very important stuff. File it away. You'll use it in physics. You'll use it in calculus. And it's a very important topic that you master here.
Learn anything at mathandscience.com.